Hello. Is it on? Good evening and welcome to the first series in our 11th annual public lecture series here at Carnegie. Thank you for finding us. I know, as you all know, we've moved from the Huntington Library. The building we've been using for the last 10 years is actually being torn down and remodeled. And so in a few years, when they have a new auditorium, we'll move back there. But this is our location for this year, so I appreciate you all finding us. We have a very exciting series this year. Normally we have a lot of talks on cosmologies and galaxies and very distant things in the universe. This year is actually a kind of a nearby universe look, I'd say. In fact, tonight's talk is the furthest away thing, and it's pretty nearby. And this is... Okay. Thank you. And so this series this year, we're going to have a talk on the next time in 2 weeks on the solar system, which I don't know if we've actually ever really had a talk truly on the solar system by one of our experts from our sister department in DTM, Washington. And then we have 2 talks later in the semester on elements, where the elements come from, including a specialized talk on elements in you'll see the nuclear age. So it should be a really interesting talk by one of the world's experts on rare earth elements. So it should be a very exciting lecture. And tonight you're going to hear about a frontier area in astronomy. This is kind of one of the future fields in astronomy, and that's a field we call transient astronomy. That is, transient refers to something that comes for a few days and then is gone. Something that's bright for a few days and then is gone. And we've known about transient events like supernova for a long time. But what we've realized over the last few years is that there's really a great diversity in these transient phenomena. And tonight you're going to hear from one of the young experts in this field, but Mansi, who finished her PhD down the street at Caltech in 2011. And she's been at Carnegie as a prestigious Carnegie-Princeton postdoctoral fellow / Hubble fellow. That's kind of the most, since most of you won't know, that is the biggest, best titles you could possibly have as a young astronomer. She's already published 89 papers, which is pretty significant because I think I'm about 15 or 20 years older than her, and I'm only about 115, I think. So she's really quite prolific. That includes 8 Nature papers. So Nature is a journal where you only really report things that are just really, truly new and exciting. I mean, it's truly outstanding. So you're really quite lucky to have her here today. We're very lucky to have her at Carnegie, and she's going to tell you kind of about this new field of transient astronomy. So let's welcome Mansi. Come up. You have your own mic, right? Let's see.
So thank you very much, John, for the generous introduction. And thank you to Carnegie Observatories for this opportunity to share my excitement for astronomy with you tonight. So very good evening to all of you. Today I'll be talking about fireworks that light our universe, and my goal is to not fall from the So fireworks that light up our universe. So the universe that we live in is a very beautiful place indeed. The sun, which is the star that lights up our day every day, is just one star amongst 100 billion stars that make up the Milky Way galaxy. And the Milky Way galaxy in turn is just one galaxy out of 100 billion such galaxies in the universe. However, even though that would add up to a very large number of stars, and you see some of the stars in the Milky Way galaxy in the background here, that's not enough. The universe is a very, very big place, and it's only getting bigger. It's expanding at an accelerating rate. So in fact, if you go out into the universe, you'll find that it's quite dark. And so, you really do need some fireworks, a candle in a dark room that will light up that dark room for you, and that would serve as a very energetic, even if ephemeral beacon of light to give you some clues to better understand our beautiful universe. So the backdrop here, so the story begins with the backdrop. This is Las Campanas mountain, a mountaintop in Chile. This telescope that you see in the picture is the Magellan telescope. This here is the Milky Way galaxy. This is the Large Magellanic Cloud. And the story that I want to start with is began on February 24th, 1987, when there were 2 people from Carnegie, Ian Shelton and Oscar they saw a star there that they didn't remember seeing before. It certainly wasn't there the night before. So what had happened? And what they found was that there was, in this very center of the galaxy, there was a very bright explosion. And this explosion, some of you will recognize, is called supernova 1987A. This one single star, in its death, became a billion times as bright as our sun. So it became exceptionally bright, brighter than the galaxy that we lived in. So most of the talk today will be talking about very, very bright beacons of light, such as the supernova 1987A, which marks the death of a very massive star. Those of you who came in early heard some music playing. This was no ordinary piece of music. What you were hearing when you came in was a supernova sonata. It was made by Alex Parker and Melissa Graham. And let me explain to you what you heard there. What you heard there was data from the Supernova Legacy Survey. This is a survey of the Canada-France-Hawaii telescope, where they just imaged 4 square degrees in the sky. So that's about that much in the sky, that's the size of the moon. So it's about 4 square degrees, that much area of the sky. And with their telescope, they just imaged that area of the sky over and over and over again every few days. And the little things that came flashing up, those were the supernovae that we discovered. So what Alex and Melissa did was that they made this composition where every note actually represented a supernova. And the loudness of the note was the distance to the supernova. So it was louder, the supernova was closer, and fainter, the supernova was further away. Then the pitch of the note actually denoted the lifetime of the supernova. So a high pitch meant a very short-lived supernova, and a shallow pitch meant that the supernova lived for a little bit longer. And the choice of instrument was motivated by the choice of the host galaxy that the supernova went off in. So let me play this one more time, so maybe you can appreciate the strange music that you heard in the beginning a little bit more. Okay, that was just so fun. This was back in 2008, 2003 to 2008. But there's been a paradigm shift in even how we discover supernovae. And let me tell you how. There's a project called the Palomar Transient Factory that I was fortunate to be part of and built during my PhD thesis at Caltech. And instead of imaging just that much of the sky, 4 square degrees, it images the whole sky. So the video you will see is, this is a representation of the sky. And the video that you will see is the area of the sky that is imaged night after night by the Palomar Transient Factory. And the color coding here is the number of images of that area of sky. So you can see very quickly that almost the whole sky, you can only see about 3/4 of the sky from any given location over the course of the year. 1/4 is unused, so you can't look there. But you can see that in the 3/4 of the sky that's accessible from Palomar, this particular survey, the Palomar Transient Factory, has imaged it many, many times, hundreds of thousands of times in some places, to look for supernovae. And what this factory that is churning out transients at Mount Palomar has accomplished is 1,925 supernovae. And let me tell you a little bit about how exactly does the supernova discovery process work. And let me just explain that based on what happened at 2 a.m. last night. So, on Mount Palomar, and I hope some of you have at least visited Mount Palomar. It's just 130 miles southeast of here on the way to San Diego, and it's open to everybody to visit. There are multiple telescopes. So there's the Palomar 48-inch telescope, which is our venerable Schmidt telescope, and that's what goes and images these huge spots of sky over and over again. Now we have a software pipeline which actually takes this data and says, hey, is there a star there tonight that wasn't there last night? And if it is, then it's a supernova. intern. And then after it does that, after these two telescopes have done their job, like at 2 a.m. last night, I got a phone call saying, okay, there's a really young supernova in a galaxy. Literally, my phone rang. And then as soon as that happened, I said, okay, this is amazing. So what other telescopes can we look at to understand what type of explosion went off? So what I did was, the first thing I did was I called up the Swift satellite. Some of the triggers, some of the phone call. It's a satellite in space which went and observed the supernova and the X-rays and the ultraviolet. Then on the Palomar 200-inch, we went and got a spectrum. Then in Hawaii, another telescope went and got a deeper spectrum. This is the Keck telescope. And then it became morning in most of the US. It was striking. The supernova was rising and it was getting more interesting, but the sun was up and I couldn't do much. So then I called up my friends in India who started to observe this in India. This whole thing got very crazy. So I look a little bit sleepy today. Please forgive me. So that's just some fun on how supernovae are actually discovered by something like the Palomar transient factory. So that number should be now 1926 supernovae since 2009. Okay, but now I want to change gears a bit. What I really want to tell you about today is not how we find the fireworks, but what do we actually learn from the fireworks? And what do we learn about the fireworks? And what have the fireworks actually taught us about the universe that we live in? So I'm going to take you on a historical journey. That's what this is the blue rocket here, the PSLV from India. And then I'll start from the very beginning and just advance in time, and then end with a crystal ball of what I think will happen in the next few years. So the very first supernova discovery, that was in AD 185 by some Chinese astronomers. I don't have a picture of the Chinese astronomer who discovered it. This is just a representation. But the Chinese people were very, very meticulous in bookkeeping. So they had kept a very nice record of every star in the sky. And in AD 185, which is a very long time ago, they noticed that there was a new star in the sky. And that was actually a supernova in our own galaxy, the Milky Way, that you could just go out and see with the naked eye. And then a few centuries later, in AD 1054, much closer to where we are, in the caves of New Mexico, there was this cave painting found which dates back to 4th of July in AD 1054. And this cave painting remarkably shows the position of the supernova and the position of the moon exactly where it should be. So this is another supernova from AD 1054 that we found even before we knew how to read and write. Fast forwarding again by a few centuries, it's only a 45-minute talk. In AD 1572, there was a discovery of a new star in the constellation of the Queen Cassiopeia. Now you notice the position of this new star labeled Nova is a little bit awkward. And what is even worse is that this is the 16th century. This is about when the Renaissance was starting. So when Tycho Brahe actually found this star, it shook up everybody. All the kings and queens and priests, everybody was very unhappy with Tycho Brahe because he told them that, hey, there's a new star in the sky. So the universe that we live in is not unchanging. It's not immutable. The Earth is not really in the center of action here. So it caused a lot of problems for Tycho, but it was indeed another supernova in our own galaxy. So let's fast forward a few more centuries, all the way to the 19th century. The picture that you can see here is actually a picture by William Huggins, who is a British astronomer, and this is the very first spectrum of a nova or a supernova. In fact, this was actually a nova in the Andromeda galaxy. And let me explain what a spectrum is. So usually you go and you take images with your camera in the sky. Sometimes you use something better than a camera. You use a prism. So you have the light of the supernova star come, you put it through a prism, and you disperse the light. So what you get is a rainbow. So you get the intensity as a function of wavelength or as a function of color. So that's what this funny picture here is. It is intensity as a function of wavelength. So it's a spectrum. And a spectrum really is the most important clue for understanding novae and supernovae. This is because the spectrum tells you three things. First, it tells you how far away is this explosion that you found. Is it in our own galaxy? Is it in a nearby galaxy? Is it in a galaxy far, far away? Second, it it tells you how fast are things moving in this explosion. Are they moving at 1,000 kilometers per second or 10,000 kilometers per second? Or sometimes even 30,000 kilometers per second. The third thing this picture tells you is what is the chemistry? What is this particular explosion made up of? How much carbon is there, how much oxygen is there, how much silicon is there, how much hydrogen is there? So spectrum really is the thumbprint or the fundamental signature in understanding a cosmic explosion or a transient. That's why I put the first spectrum of an explosion. So remember that one, 1866. And then fast forwarding to the 20th century, in 1932, and I hope some of you recognize this picture from the Huntington Library. This here is the logbook of Edwin Hubble. Edwin Hubble, when he was observing with the Mount Wilson telescope, would meticulously write down in his notebook one line per observation of what he was actually taking pictures of. And you can see he's taking pictures of one thing at a time, it goes on and on. And then suddenly something happens here. There's lots of scribbles here. He got very excited. And what you will realize is that it says here, confirmed nova suspected. So this was the first discovery of a nova in the Andromeda galaxy. And around the 20th century is when Hubble realized that Hubble, along with other astronomers, realized that these new stars that people were just calling nova stella, actually fell into two very distinct categories. There were some explosions that were somewhat wimpy. They were lower class novae, according to these old historic documents. And then there were some explosions that were much brighter. So they were some sort of upper class novae. And Hubble was really bothered there was no middle class novae in this story. But anyway, they didn't choose these politically incorrect names. They decided to name the wimpy explosions nova, and they decided to name these really bright explosions supernova. And to give you context of the difference in brightness, a nova is 1,000,000 times as bright as our sun, and a supernova is 1,000,000,000 times as bright as our sun. So that's it for history. Let's fast forward to the 21st century. Let's move on to AD 2005. Now 2005 is a very special year. This is the year I came to graduate school. Okay, so this is not very long ago. This is only 8 years ago. And in 2005, obviously now the century is gone, and we've been looking for new types of explosions for many, many centuries. So if you combine all these new stars that have been discovered, by this time we already knew about 1,000 classical novae and 5,500 supernovae, which are denoted by these two gray boxes. It was very clear that there were these three different explosions: classical novae, 1,000,000 times brighter than the sun, and thermonuclear supernovae, which are type 1, and core-collapse supernovae, which are type 2. And I'm sorry, I should backtrack a little bit and explain what this diagram here is. So this diagram here is a framework of cosmic explosions. So it asks a very simple question that how bright did the explosion you just saw get, and how long did it live? So if it was faint, if it was only 1,000,000 times the sun, it would be there was candle about it. That's where 1,000,000 times the sun is. If it was much brighter, it would be higher up in this diagram. And then if you ask the question, okay, how long did it last? If it lasted for 1 day, it would be in the left end of the diagram. If it lasted for 10 days, it would be somewhere in the middle. And 100 days would be somewhere in the right. So it's just luminosity and time scale. How bright did it get and how long did it live? So let me tell you a little bit more about what we know and have learned from novae and supernovae. First, what is a nova? How do you get an explosion that is 1,000,000 times as bright as the sun? So the picture here shows you how. The little white thing here is what's called a white dwarf. It's a very, very dense, dead star. And what this white dwarf is doing is stealing material from its companion red giant star. So as this white dwarf steals material from this red giant star, when it accumulates something like 10,000 solar mass of material, it's enough stuff on its surface that the pressure becomes somewhat uncomfortable and high. So on the surface of this white dwarf, which is this very, very dense old star, you get some burning. So you get a thermonuclear runaway, and the explosion that you get is called a nova. It's not a very big explosion, it's only 1,000,000 times as bright as the sun. But and it doesn't destroy the red giant. So the important thing to understand about classical Novae is that it can happen again. We can have an explosion today, another one 10 years from now, or another one 10,000 years from now. Really depends on how greedy that white dwarf was and how much material it was stealing from its companion. Now let me tell you about supernovae. And here's a video explaining to you how a type 1a supernova happens. So at least some of you must be wondering, hey, I'm showing you the same picture again. It's a white dwarf and a red giant, right? So what's different? Why does this explosion become a billion times as bright as the sun? This is because this white dwarf is awfully greedy. Instead of stealing just 1/10,000 of the solar mass material, it stored almost a tenth to 1/2 a solar mass of material, and it made the white dwarf very, very heavy. The white dwarf crossed the maximum mass that it could possibly support itself with. So when the white dwarf exceeds something called 1.4 solar masses, which is the absolute maximum that the two forces in the white dwarf can balance itself. So one force is gravity, which pulls the white dwarf inside, and the other force is a quantum mechanical force called electron degeneracy, which is an outward force. So these two forces have to balance for the white dwarf to be able to hold itself together. But when white dwarfs get very greedy and steal material either from a red giant or another white dwarf, and they exceed this critical mass of 1.4 solar masses, they just completely explode. So this is no small burning, it's a complete destruction or detonation of that white dwarf. So it gives you this very, very high velocity, very, very energetic beacon of light that we call a type 1a supernova. Now that's an extremely useful thing, because if you know that you have this really bright beacon of light, and you don't have one of them, you have thousands of them, and they all happen in different galaxies at different distances, then you can tell how far away something is just by using these explosions as standard candles. So right here you have a yardstick with which to measure the universe. And this is being done. Type 1a supernovae serve as beautiful standard candles, and they've been used to measure the size of the universe. And what people found was that the universe was not only getting bigger, it was getting bigger at a faster and faster rate. The universe is actually accelerating in size. And this fundamental discovery was important, appreciated as important by the Nobel Committee. And the Nobel Prize in Physics in 2011 was awarded to 3 astronomers here for this very discovery. These astronomers accepted this prize on behalf of hundreds of astronomers who've been working very, very hard to make this very precise measurement of the expansion size of the universe. Okay, so that's about Novae and thermonuclear supernovae. So let's now understand this other big grey box here called core collapse supernovae. So core collapse supernovae are completely different. They have nothing to do with white dwarfs. They are the deaths of very massive stars. So when a star is more massive than 8 to 10 times the sun, then it does more than the sun does. Right? In terms of, if you look at its core, the sun is burning hydrogen into helium, and that's what's giving us all the light that we enjoy every day. But when a star is more massive than the sun, then it does more than that. So after the hydrogen gets burned into helium, it burns the helium into carbon, then the oxygen into silicon, the silicon into iron. And as it goes through all these phases of nuclear burning in its core, it eventually reaches iron, and at that point it gets stuck. Because iron is something that you cannot burn efficiently. When you try and burn iron, it needs more energy to burn than the energy it gives out. So that's no good for the star. So when it gets stuck at this stage of iron, the core actually collapses. And when the core of a star, much more massive than the sun, collapses, you get a core collapse supernova. And the picture that you see here is actually the picture of one of the historic supernovae from our own galaxy. This is the remnant of that supernova that you see here. So what are core collapse supernovae good for? You can see I've made a big gray box to tell you where the few thousand core collapse supernovae are. They are by no means standard candles. They have luminosities all over the map. They are very, very diverse. There's a whole zoo of core collapse supernovae. Don't even get me started on the classification schemes for them. But they're good for something else. They are so energetic. They again become become a billion times as bright as the sun. And the explosion there is so energetic, the temperatures and density there is so remarkable that most of the periodic table is actually synthesized in the core supernova explosion. So you can see that most of the universe is very boring, it's just hydrogen and helium. And then there is some burning in the cores of massive stars that brings you up to iron. And then in the supernova explosion, you said we synthesize some more elements. So to put it more eloquently, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies, we're all made inside the interiors of collapsing stars. We are all made of star stuff. So that's Carl Sagan's quote. So he certainly liked core collapse supernovae. So the question is, what else is there? There's Novae, there's thermonuclear supernovae, core collapse supernovae. We now have something that we can do cosmology with, measure the size of the universe with. We now have something that will help us fill up the periodic table. That's great. So what other types of explosions are out there? And it turns out there's actually many more explosions out there, especially in between a nova and a supernova. These middle class novae that always bothered Hubble since the 1930s, they're finally finding them. So these are explosions that are 10 million or 100 million times the sun. So this picture that you see here is the life cycle of a massive star. What was the initial mass of the star, and what will it end up as? So for example, the sun will just end up as a white dwarf. It won't give you a core collapse supernova explosion at all. But a star 10 times the mass of the sun does give you a particular flavor of core collapse and ends up as a neutron star. When a star is 100 times as massive as the sun, it would result in a spectacular explosion, a really, really bright explosion, such that it actually has no remnant. This is a pair instability supernova where even when the core collapses, you don't end up with anything in the center. It's completely obliterated. I promised I'll tell you a little bit about the birth of black holes. So that's somewhere in this middle region here. We don't quite know where. So when a star is about, say, maybe 30 or 40 times the mass of the sun, when its core collapses, instead of getting something called a neutron star, it's actually so heavy that you get a black hole. And the reason you get a black hole is because there's material that's falling back on top of that rotating neutron star. So when a black hole is born, you would expect that a more massive star is making a black hole, it should be a brighter explosion, right? But it turns out it's actually backwards. The gravity well is so deep in the black hole that it's stealing material that would otherwise give you power to explosion and make the explosion brighter. So with the ejector from the explosion actually falling inwards instead of outwards, you can actually get a fainter explosion for a more massive star, or what I call a gap transient. Another place where our understanding of stellar evolution is incomplete is when two stars emerge. I told you about the novae and supernovae that come from white dwarfs. Well, you could also have a big white dwarf and a little white dwarf, which is a helium white dwarf and a carbon-oxygen white dwarf. And that would give you a middle-class nova, something that's 10 million or 100 million times the sun. You could get two neutron stars or a neutron sun black hole merging, and that would give you gap transient. Or take any two random compact objects and try to merge them, and it would be a gap transient. So the question really is, why is it that as late as 2005, we didn't know about any gap transients, even though nature should have made lots of different types of gap transients? So this is simply because astronomers are exploring the universe, which is very big, and the first thing they find is the things that are easiest to find. You always pick the lowest hanging fruit first. And let me explain how that applies here. Both novae and supernovae are very easy to find. So supernovae are easy to find, well, obviously, because they're so bright that you can find them in galaxies far, far away. But there's only about one supernova per century per galaxy. So you need at least 100 galaxies to find one supernova per year. Of course, now we have the capability of searching many more than hundreds of galaxies, so we find a lot more than one supernova a year. Now, novae, on the other hand, they are very weak. They are very hard to find. They are only a million times as bright as the sun. But they too have been found in the thousands, and that's because they are much more populous. In any 20 novae per year. So even if you had one galaxy, you would get 20 novae per year. If you had a few, well, you'd have hundreds already. So that's the reason why novae and supernovae have been the easiest to find, the lowest hanging fruit for fireworks that light up our universe. So the next thing I'm going to tell you is how we've actually gotten to harder to pick fruit, the ones on a little bit higher branches. Because now with projects such as the Palomar transient factory, we're searching tens of thousands of galaxies. So we're able to find supernovae that are fainter, faster, and rarer than anything we've seen before. So the same diagram that I showed you, which is how bright did the supernova get, and how long did it live, today it looks like this. And you can see this is much more exciting, much more colorful at least than the previous picture. And this is why it's a really exciting time to work in this field. There's literally a renaissance of sort, because from 3 types of explosions, we suddenly have a zoo of all types of things where you're finding 1 or 2, and these things look like nothing we've seen before. There's not 1, but 2, 3, 4, 5 different classes of explosions, which are completely new and only discovered in the past few years that we are starting to unravel. And each of these explosions represents some different physics, some missing piece in our understanding of the life cycle of a star or how 2 stars merge, and filling in our understanding of chemistry as well. So let me now tell you a little bit about each of these new types of explosions that have been so much fun to discover and follow up. So first I start from the red end of the diagram. So these are all very long-lived and low luminosity explosions. So these are what are called intermediate luminosity, because they're in between supernovae, red transients. So what was cool about these transients when we first found them was that there was no progenitor star. So we saw an explosion, but if you looked at the galaxy before the explosion happened, there was no star there. So what blew up? Something blew up. We don't quite see what blew up. And these were very deep images taken with the Hubble Space Telescope. So that was a bit odd. But luckily another Carnegie fellow, Jose Prieto, made this amazing discovery where he found that the star was actually there in the red images taken by the Spitzer Space Telescope. So the Spitzer Space Telescope actually images in the mid-infrared, and these stars that just weren't there with the Hubble Space Telescope showed up in the Spitzer Space Telescope. So if you combine these 2 pieces of information, it actually tells you that the star that blew up was an 8 to 10 solar mass star. So it is right in the middle of the stars that make white dwarfs and the stars that make neutron stars from regular globular supernovae. And if you looked at what the explosion of these stars resulted in, the explosions were also very red. So this here is an intermediate luminosity red transient, which is a zoom in of this region, that occurred in this galaxy Messier 99. And if you looked at what the explosion properties were, the explosion was very, very long-lived and got redder and redder as a function of time. So if you look with the blue filter in your camera, and you looked at blue light, the explosion died off in 40 days. It was gone. In the redder bands, it lasted for hundreds of days. And in the mid-infrared bands, with the Spitzer Space Telescope can access, they lasted for at least 4 years and counting. They're still there. And then I promised you some spectra, right, which is the thumbprint of what these events are. And the spectra here showed calcium, some hydrogen, and the velocities here were larger than a nova and less than a supernova. So if you put together all of these different clues, what we are seeing here is really that missing piece in stellar evolution between 8 and 10 solar masses. Less than 8, you get a white dwarf. More than 10, you get a neutron star from a globular supernova. Between 8 and 10 is where you get this electron capture from this very red transient. Another very red transient is something called the luminous red nova. A luminous red nova is actually the merger of 2 stars. So there's a beautiful object that was observed by the Hubble telescope where they were monitoring a star for 10 years. They were just looking at this. I'm looking at many other stars too. But this particular star, you could see that it was going around another binary, and you could measure the period of this, of how much time does it take to go around. And over the course of 10 years, you saw it speeding up, speeding up, speeding up, and as soon as that period declined to 0, you saw a very, very large another type of red gap transient. So let me play this movie again to explain what light echo is. So when the two stars merged, there was a shock that went out, a very bright light. And when this light went out, the surrounding media, the dust absorbed some of the light and re-emitted it. So that's why you see the circles of dust. And if you image it a year later, the shock moved further out, so you get a bigger ring of dust. For 1 more year later, moves further out, and you get a bigger ring of dust. So this is images by the Hubble Space Telescope of the light echo of VA3 at Mon. Okay, so this is just two types of gap transients. These are the easiest to study because, as you can see on the right end of the diagrams, they last for a few months. So you don't have to wake up at 2 a.m. for these, which is good. Okay, so the next category are calcium-rich gap transients. These are a real mystery, and they're really mysterious because of where they happen. We now know, just in the past few years, from 0, we now have a big sample of 8 such transients. And the strangest thing about them is they like to occur in the middle of absolutely nowhere. It's very surprising. For example, here's one of the such transients called ETA-ONDAB. And this transient actually seems to be coming from this galaxy. But this distance here is huge. To put it in terms of light years, this distance here is 120,000 light years. So why would a star wander off so far away from its host galaxy and then decide to explode in this really weird way, which is neither a nova nor a supernova? So the first one, we were just scratching our head, a little bit confused. And then we kept finding them over and over again. So there was another one, which would be anything in either this galaxy or this galaxy or this galaxy. But it was hundreds of thousands of light years away from any one galaxy. Then most recently, we found another such event, the same characteristics, the same bizarre explosion characteristics, which happened in the Coma cluster. So there were literally hundreds of galaxies that were at the same distance as a supernova. It could have come from any one of these hundreds of galaxies, but it was very, very far from any particular galaxy. So these transients consistently have happened in the middle of absolutely nowhere. And what do they look like? So this is again a light curve, where you're measuring the brightness of the transient as a function of time. So you can see that this transient got brighter over the course of 10 days and then declined over the course of a month. And you can compare this to the type 1a supernova, that energetic standard candle that I told you about. It's much weaker, so it's very good in terms of its faintness, and it's much faster than a type 1a supernova. But all of these calcium-rich gap transients, they all line up about the same region of this diagram in terms of their light curves. But they all happen in the middle of nowhere. But why do I keep saying calcium-rich? It's because of the spectra. So if you look at the spectra of these transients, so now this is how brightness is a function of wavelength, or a function of color. And when you see a bright line here, that actually tells you which element is emitting the strongest. So you can tell the chemistry of the explosion by looking at these wiggly lines. So this line here, the black lines here are the calcium-rich gap transients, and clearly they have this one warming feature, which is calcium. And if you compare it to the gray library of supernovae, then you can see that this spectrum looks very different from these other spectra. First of all, there's not much ejecta in this class of events. And whatever little ejecta there is dominated by calcium. So why is that? Why do you get these calcium-rich gap transients in the middle of nowhere, in the middle of galaxy groups, in the middle of galaxy clusters? So these gap transients are John's favorite because he made this amazing connection that if you look at this problem, there's a calcium problem that's been around for a decade for X-ray astronomers trying to measure the chemistry in clusters. So what X-ray astronomers do is went out, looked at some clusters, and in the intercluster medium measured what the elemental composition should be. So this solid line here, the solid black line here, is their measurements. There should be so much silicon, so much sulfur, so much argon, so much calcium, so much iron, and so much nickel. But the problem that the X-ray astronomers were facing was that, okay, all these elements are made in supernovae, but if you add up how much of these elements are made in type 1a supernovae and overlap supernovae, which is all we knew about until a few years ago, they could explain all the elements except for calcium. They could only make up half of the calcium in the known types of supernovae. So what John did was added these calcium-rich gap transients to this figure, and he said that, oh, calcium-rich gap transients can actually account for that missing calcium in X-ray clusters. So that was pretty fun. The gap transients, which is 8 of them, are helping solve an important mystery of what is the chemistry that makes up clusters in our universe. So let's understand another category of gap transients. These are called 0.1a explosions. So now you can see I moved on to the left end of the diagram, the brightest. These are the brightest gap transients and the shortest lived gap transients. So these are the ones that really you have to wake up for, right? Because they rise from nothing to peak in 6 days, and then they divide exponentially on a time scale of 5 days. And they're faster than all these other dash lines, they're faster than any other supernova that you can think of. This is again a spectrum, so you can see that all of these figures, you can see which elements each of these figures is made up of. So you can really tell what the chemical composition of this particular type of explosion is, and you can measure the velocities. And eventually what you learn from them is that there is a set of about 7 properties here that the light thermal spectra obey, and it is most likely a 0.1a explosion. So let me explain the name first. What is 0.1a? So Professor Lars Wilston, who's a professor at UC Santa Barbara, came up with this name. So he was studying the case where you have a big white dwarf, a carbon-oxygen white dwarf, and a little white dwarf, which is a helium white dwarf. And these two white dwarfs, this big white dwarf and smaller white dwarf, are going around each other in a period that is shorter than 1 hour. So they finish one trip around each other in less than 1 hour. So that's very, very short as far as white dwarf binaries go. And the little white dwarf is transferring material onto the big white dwarf. So in such a system, when all the material from the smaller white dwarf goes onto the big white dwarf, if the time scales are such that the nuclear time scale is short, you would get an explosion. And this explosion would be very different from a type 1a explosion, in that everything would be scaled by 0.1. So a type 1a explosion, take the brightness of a type 1a explosion, divide by a factor of 10, you get the brightness of a 0.1a. Take the time scale of the explosion, divide by a factor of 10, and you get a 0.1a explosion. Same thing with ejector mass, etc., etc. So Lars Wilston and his student Ken Shen made a list of predictions of what would happen when you have this big white dwarf and little white dwarf merge. And it just turned out that these papers were published before we found these 2 examples of 0.1a explosions, and every single property that they predicted actually worked out. So let me just show you a movie. The movie is cheating a little bit because these 2 white dwarfs are the same size. What actually happens in a 0.1a is it's a small white dwarf and a big white dwarf that's merging. So you can see that as they come closer, they start spinning faster, the period gets shorter, and eventually they will merge. Okay, so that's it for gap transients. The question now is, what's next? What if I took out my crystal ball and said, okay, what are we going to find next? Now that we're actually finding things that are fainter, faster, and rarer than supernovae, is there something that's even fainter, even faster, and even rarer? One example of such an explosion would be a neutron-star merger, or a neutron-star black hole merger. When this happens, then instead of getting something like a supernova, which is 1 per century of a galaxy, or some of these other gap transients that I've described, which are 1 per 1,000 years of a galaxy, you get these rare explosions, 1 per 10,000 1,000 years from galaxy. So they're extremely elusive. And the only hope of finding them by AD 2020 is that they are very, very strong gravity emitters. And they can help us fundamentally understand gravity better. So gravity is a force that we all know about. It's what makes the Earth go around the sun, we go around the Earth. It's what struck Newton on his head when the apple fell. Don't know what that happened. But our picture of gravity has actually become much more sophisticated. We now think of gravity as what gives shape to a four-dimensional fabric of space-time. So if gravity is what's giving the shape to something that's four-dimensional like space-time, there should be waves, right? There should be gravity waves. Yet so far we've not seen any gravity waves. Our only hope of seeing such gravitational waves are when extreme events such as the merger of two neutron stars or the merger of two black holes, which are very, very dense and compact objects, happens. And this would be very fundamental. We really want to understand understand gravity better. So about 1,000 physicists have been working very hard to build an instrument that can actually go and measure these gravity waves when these neutron star mergers happen. And they've undertaken this heroic effort. This here is a picture of an interferometer in Hanford, Washington. They also have one in Louisiana, and then one in Italy, and maybe one in India and Japan in the near future. And they are making a measurement which is 1 part in 10 to the 19. So it's a very, very precise measurement where they have two interferometers and a little piece of glass lying in the middle here, which should move by that small fraction that they can measure. But they hope to, their experiment has reached a stage where by 2017 or 2018, detection of gravity waves should be routine. They should be able to find one neutron star merger every month. And that's fantastic, right? Because that will really help us understand gravity. But some of you might notice that there's a weird golden ring around these two events. What's that all about? The reason I have that ring is because even after this heroic effort that spanned decades and there have been thousands of very hard-working physicists to make this possible, once they start finding these neutron star mergers, it will be somewhat unsatisfying. Because they will be listening to these mergers at a frequency of 150 Hz. So that's a frequency that the human ear can listen to. But they won't be able to tell where it happened. They won't be able to actually see the explosion. Because they'll be able to say, okay, because they can only hear it, it's coming from somewhere there in the sky. And that somewhere there is a very, very big circle. So you wouldn't know where it happened, you wouldn't be able to see it. And astronomers, as you know, absolutely love photons and want to be able to see these events. And they're especially eager to see neutron star mergers because these are such extreme events that that's where gold is synthesized. There's something called R-process nucleosynthesis, which happens in very neutron-rich material, and that's where a very important element that I'm sure all of you like, gold is made. So we want to find out the site of gold. And so astronomers have been preparing for this era, which will be 2017, 2018 is around the corner, to be actually able to identify and search for these electromagnetic waves from these neutron star mergers. So in a sense, we will see that sound. There are a lot of challenges because if you just say something blew up in that general area of the sky, I just told you about a zoo of explosions. There's a lot of explosions in the way, both in our own galaxy and in galaxies behind the galaxy in which the actual neutron star merger happened. So it's a very tough problem, and lots of people are undertaking extensive simulations to try and understand how to find that needle in the haystack. And of course, telescopes are gearing up. This is pushing the limits of telescopes that we can use to be able to uncover such an elusive event. So here's just an armada of telescopes that I think will play an important role in answering this question. So I'm optimistic that we will actually be able to see the sparkling gold when we hear the gravity wave as early as 2020, maybe even sooner. So with that, I'd just like to thank you all for your time and attention and take any questions.
Fascinating. Calcium doesn't sound like one of the normal every 4 nucleon on products, but does the fact that you see a lot of calcium tell you not only that it's making a lot, but also that the material is in a state that it's primed to radiate? Does it tell you a lot about the state of the atmosphere? Is something unusual about that aspect?
Possibly. So the question is about the calcium-rich cap transients and whether the calcium is actually telling you something about the atmospheres in which this happens. Well, our best guess at this point, we know about the environment. That's one thing we have a solid clue on. The environment in which this happens is a very, very dead and old environment. So whatever is blowing up here is a very old dead star, probably a white dwarf, a neutron star, some sort of compact dead star. It's not a young massive star that's blowing up. At that point, the stars are so cold and that they don't have much of an atmosphere. But definitely the calcium should be a clue since it's a product of explosive nuclear synthesis. It should be a clue into what exactly blew up. But it's an open question and a complete mystery as to exactly what blew up to give you this calcium-rich cap transients. Because why would something always happen with the globe and never happen where all the action is where all the stars are? So it's a difficult question.
Any other questions? In back.
What leads you to the goal of merging the two neutron stars, creating gold versus type 1 supernova creating that?
That's a great question. So when two neutron stars merge, you have very neutron-rich material. This is a very, very extreme event. And when you have that, you can have something called the R process, which is a rapid process. And when that happens, you can synthesize elements that are much higher up in the periodic table than in a normal supernova. And the site of this R process is highly debated. Where does this happen? And in terms of the theoretical framework, we've never seen neutron stars merge, but theoretically, we expect that when neutron stars merge, there are enough neutrons there. It will be very neutron-rich. You go through this R process nucleosynthesis, and you'll get a lot more than gold. You'll get the lanthanide series, you'll get a lot of elements in that part of the periodic table. I just picked gold as an example, as an element that everyone can relate to here. There'll be a wide array of elements that will be synthesized. So when you get a spectrum of one of these events, it will be amazing because you actually see lines in that spectrum that you've never seen before. So there'll be bumps and wiggles there that you actually don't recognize. That could most certainly happen as well. And this type of an explosion could happen with a neutron star and a black hole, making another black hole, or two black holes as well. Right. So you could, in the center, you could certainly get a black hole. But when it gets created, there's also stuff that gets thrown out. And the stuff that gets thrown out is the ejector that would synthesize these elements like gold and help you listen to these as gravity waves. So even when these two things merge, no matter what happens in the center, it would send off this ripple in the fabric of space-time that it would detect as gravity waves.
A couple questions now.
Yeah, when you said the stars greater than 100 solar masses have no remnant and explode, is that from modeling? Is there any observational evidence of that?
Great question. So that is actually, so again, only recently there was a graduate student at UT Austin, University of Texas at Austin, Robert Kirby, who found a class of explosions called luminous supernovae. These were rare explosions and even brighter than supernovae. So if you remember in my figure, they were in the top and right end of the plot. Let me go back to it. So these explosions are here, luminous supernovae. And what these luminous supernovae are extreme explosions where if you actually go and start to measure what was the mass of the star that exploded, then you can go backwards and you can see that if something created 5 solar masses of neutron. That's a lot of neutron. Usually you get half a solar mass or 1 solar mass. So if you trace how big did the star need to be to generate 5 solar masses of neutron, it would have had to be a 100 solar mass star. And the only way you can explain such a luminous supernova is through through something called pair instability explosion, which is an explosion which generates electron-positron pairs. But without going into the details, It is an explosion that is extremely energetic and extremely luminous that destroys the star in its entirety. That's the best hypothesis that we have in terms of explaining an explosion that is so luminous that it's on the top end of that diagram, much brighter than anything we've seen before.
Is there any one of those telescopes that would be particularly helpful for the crystal ball?
Any one of those but the big one? That's a tough one. I think no one telescope can do it. It's a very tough problem. Because the predicted counterpart, which would be the transient that's expected, is supposed to be last only a few hours or a day. And at that point, and it's supposed to be very faint. So at that point, you really would put all your eggs into that basket. No one telescope is going to do it for you. So at least I believe that this would have to be a coordinated effort around the world, whichever latitude, longitude you're on. So you can respond in the fastest amount of time. As soon as you hear the gravity wave, you have only a few hours to respond and get a telescope pointing in that whole region of sky, wading through the haystack and finding that wave. It's a very tough problem. But I think we can do it. It's not so tough that you can't do it.
Last question.
Between the thermonuclear supernova and the classical nova, is it mainly the distance between the white dwarf and its large nearby stars, trade material that falls onto it, accretion distance? Is it how close it is that limits the amount of material that falls on it, or is it the size and its ability?
Great questions, all of those things. So the difference between when you get a nova versus when you get a thermonuclear supernova is how much material you're stealing, which is directly related to the rate at which you're stealing them. So how much material do you, so it's called the rate per year. How much mass do you steal from your companion per year? So the rate has to be, it can't be too high, because if you do that, then you will accrete the material, and as soon as you accrete a little bit of material, it will burn off. It can't be too low, because it will take forever to accrete enough material to blow up as a supernova. So the rate has to be just right to actually build up to 1.4 solar masses, and not have a nova in between, but be able to reach that maximum mass and then explode as a supernova. Another thing that matters is the composition of the white dwarf, whether it's a carbon-oxygen white dwarf or an oxygen-emission white dwarf. So the chemistry inside the white dwarf also matters. But like I was suggesting, how close is the companion, what is the companion? Those are all play an important role, or all details that really determine when you get an explosion, whether it's nova or supernova or something like this altogether.
I'm sure Mansi will be happy to hang around if anybody has any questions you want to ask, please come up. Let's thank her again. We look forward to seeing you on the screen.